Okay, thanks everyone. So this is a modified version of the talk that I've been giving. So hopefully I get to share more fun things than when I'm asking for a job, which is better. So my title is Synergy of Prediction and Control in Model-Based Reinforcement Learning. And this is kind of a backtracking from the things that I want to be thinking about, covering all the stuff that I've worked on in my PhD. So as Chris said, I showed up and I was kind of sold the vision, and whether or not that's fully reality, of kind of autonomous novel robotic platforms. And like what I wanted to do was come in and figure out what we can do with these systems, and then also like, okay, how do we actually control these systems that we're hand assembling under a microscope, and what can we do with them? So I'll talk about a few robots, but the ones on the left here are a bunch of micro robots from Chris's group here, whether it's a jumping robot, a walking robot, and the Ionocraft, which I spent a lot of time on, which uses high voltage to generate a ion thruster, which is very fun. And there's some characteristics about novel robotic platforms that kind of make generating controllers more difficult, or at least different. And when you're trying to demonstrate control for a first time, this is a really different control problem, where what you have is you really don't know the system that you're studying that well. So you don't have a strong prior in the dynamics, and that makes it so that you're not really going to be able to simulate the system as much. And then, as I've kind of said, there's a high cost per test because I have to spend 2 hours over a microscope to actually assemble this before I get to test it. So there's a lot of frustration when you break these things in silly ways, but that's bound to happen. So kind of to mirror this, the solution that we're looking for needs to have a couple of properties, and those are that it needs to manage kind of changing or uncertain dynamics. So it needs to be able to generalize across a spectrum of dynamics that these robots can take on, and then be extremely sample efficient. So what little data that we have, we need to actually be able to use that to generate a controller. So to take this into kind of the video that I started with, I showed up and was given this wildly exciting video of a open source flight of Ionocraft, where you can see that it is pushing itself into these wires. It's amazing that it lands upright, and this is was more than enough to get a paper accepted at the time. And kind of I'm left with these properties and left to think about like, okay, how do we actually generate a controller for these robots? So as a electrical engineering student, I'm like, okay, like, there's a whole spectrum of things that we can try to do, and they encompass things like system identification with state space methods and be coming straight out of linear systems, or even just kind of trying to incorporate some prior of the dynamics into doing PID tuning, which is what people do in the real world. It's like, okay, it seems like we should be able to make that work. Then some exciting things I was starting to hear about, which are like in this reinforcement learning area, which are model-based RL and model-free RL, which are kind of trial and error learning and incorporating that understanding to learn about the environment over time. And you can break down these methods into different classes, which would be model-based or model-free, whether or not you're learning a transition model of the environment as part of the process. There's analytical methods where you're trying to actually write down equations for the world and use that to solve them. And then there's kind of these iterative methods that are data-driven and don't require hand engineering to actually get a solution. So kind of like the first motivating question I had to ask myself is, why may we want to use machine learning for control, and what is missing from existing practices in robotics? And something that I've come back to a lot now is that these robots generally lack the ability to really generalize in uncertain environments. Like you could engineer them in a lab, but the failures that we're seeing are just, we can't take that one step further. And I want to see robots that can kind of incorporate what they're seeing in real time to then become more intelligent and solve these tasks that ostensibly look simple. So once we kind of sold ourselves on using machine learning, which is easy to do in 2018, given everything that you're hearing at Berkeley, it kind of came down to the question of like, why would we use a model-based method or a model-free method? And generally, there's a set of trade-offs between incorporating a structured knowledge of the world versus not, and that kind of is reflected on the controller that you're going to generate. So model-based methods are known to be sample efficient, be able to generalize across the dynamics that your robot can encounter, but they're a bit harder to implement in terms of like how much engineering needs to be done and pretty computationally intensive to use. While model-free methods they generate these policies that are tough to actually interpret, but they use more data to get there. But the process of doing that has been relatively refined. So more people are doing out of the box applications of model free RL just because the code is a bit easier to use and has had more successes. But there's really a lot of compelling reasons to try to reach for model-based methods. And one that I've been looking at more recently is that if you look at what Boston Dynamics is doing, this is purely model-based control in a certain environment. And then mostly what I'm interested in doing is kind of transitioning this model-based control to then handle the uncertainty of the real world. So we can kind of get the best of both worlds, which is robots that can have this type of behavior, but in environments that they're encountering for the first time. So to kind of backtrack some of my logic from now onto the decisions that I made during my PhD, we converged on this topic of model-based reinforcement learning, which is an iterative framework of kind of trial and error learning when we're learning a structured model of the dynamics as the agent improves. So kind of while the agent is acting in the world, what it does is it acts in the environment that's from some policy or some control law. And by taking those actions, it collects a bunch of data. With that data, it learns a model of the dynamics. The equation shown here is maximizing the log likelihood of a learned model to try to fit a distribution to the transitions that we have. And once you have a model, you can then use that to plan actions in some way to maximize rewards. So again, this optimization shown here is just a finite horizon where we're choosing the best action to maximize reward. And I'll kind of talk about next what that framework actually looks like and what you might need to Google if you want to actually try to implement this approach. So I've started by kind of motivating model-based RL, and I'm going to then go a little bit deeper into a method that I used at length in my PhD, an example for actually controlling a robot, and then kind of some more theoretical contributions to the field. So if we have a dynamics model, we can kind of formulate predictions like here. We can take the current state, we can add some delta state or some one-step transition from the current state with the learned model, and we can get the next state. And the question is, how do we predict further into the future? Because most of the tasks that we want to solve are more than one step in the future. So what we can do is we kind of can repeat this prediction. So what you have is a bunch of compounded network passes, and this will let us kind of predict into the future with a learned model. And what we want to then do is figure out how do we actually use this for control. So again, there's a lot of compounded network passes, and I'll talk later about how that'll actually impact our decisions. And the question is, once we can unroll trajectories with respect to some policy or some action distribution, how do we actually use this for model-based reinforcement learning? And kind of the general class of methods that do this are sample-based model predictive control on a learned model. So we have some learned model, we sample a bunch of actions, we propagate them into the future, and then with those simulated trajectories, we can make a decision. So what we do is we start with this unrolling. From any initial state, we'll unroll a bunch of trajectories. And then what we'll do is we'll look at the proposed actions that generated those trajectories. We'll pick the trajectory that has, quote unquote, the highest reward or the best performance. Then we'll go back to the real world, and what we'll do is we'll execute an action. And in reality, we can look at the difference between the chosen sequence and either what actually happened or what we might expect to happen in a simulator. So there's always a discrepancy between the executed actions and what we expected. And then this is kind of one step in the environment. And if we repeat this stepping process over time, we'll retrain the dynamics model. And that's kind of where the reinforcement learning aspect comes in. And we have a really simple kind of intuitive reinforcement learning algorithm. And in my work, we've kind of dove deep on a few challenges that this has. So the first one is this compounding error over long horizons. When I showed you how we actually predict into the future, which is a recursive function pass, that tends to accumulate a lot of error over time. And there we're kind of playing a game where we're balancing between the error that we're seeing and the fact that we want to look far into the future to see the most reward that we can see. And then a second issue that I'll go into more detail is that it's really hard to know, like there's no guarantee on the fact that if you have an accurate model, if it'll actually be useful for performance. And kind of optimizing different components of a modular system separately in hopes of one central goal is never going to actually be theoretically guaranteed. So let's go into an example where we use sample-based model predictive control to control a robot, and then I'll go more in detail from there. So if we go back, this is another photo of the Ionicraft, and I wanted to use model-based RL to control our Ionicraft for a very long time. This was a long goal, and the first sidetrack that we took was to say, okay, if this robot has 4 thrusters, it has an IMU on board, what else can we control that's like this? And we went off and got a commercially available, very small quad rotor called the Crazy Fly. Has the same IMU on board, has 4 thrusters. It's like, okay, this is a very conceptual match to what we're trying to do. So we set up a learning system where we were applying direct low-level controls to try to create a stability controller. So we weren't looking at trajectories. We just wanted to not crash a quad rotor. So what we do, the task was to minimize pitch and roll, so kind of keep it flat in the air. And to do so, we read the onboard state values from an accelerometer. An accelerometer will give you orientation in space and accelerations in terms of the rotation or a side-to-side acceleration. And in order to control that, we sent direct motor voltages to these propellers here. And we wanted to know, like, can we just replace these internal controllers? We had turned the PID controllers off. And starting from this vision, there was a long journey into seeing if this actually worked. So this is one of my first additions from the normal job talk, which is we were stuck comparing to random controllers for a really long time. So we spent like a month doing things like this and seeing if it actually worked. And there's a lot of interesting things about quad rotors that I could talk about, but essentially the ground, if you have a quad rotor that's close to the ground, the force will create like a cushion underneath it. So it'll kind of always look like it's decent no matter what you tell it to do. So the next step was really to like, okay, launch this thing into the air. We just like made it apply max force for a few seconds to get up and then see what happened. So then the learning process is really different from there. But there's definitely a lot of hurdles to get to this point, which is like, there's just a little bit more force in these videos to get it off the ground. It looks honestly the same now that I have them back to back. But what happens is that over time, it both gets itself higher in the air and then learns to control itself. You can see in this video that I've watched many times that there's a lot of drift. That's because we're really only trying to not flip over the quad rotor. And this was a really exciting thing to actually have one of the better flights on video. The other cool mode was that it figured out it wouldn't flip over if it just used a lot of thrust, and it would go crash into one of these ceilings, and then I would catch it before it hit the ground and I had to start over, which is fun. So I was one of the few people to actually start doing reinforcement learning work in the real world. On one hand, I wouldn't recommend it, but I think that it also makes you actually learn how to do things, and some people don't do that much now. So shots fired anyways. But some lessons was kind of takeaways were that there really wasn't many demonstrations of model-based aerial and rail robotics, and I didn't realize this going in, but still to this day there are few of them. And working on quad rotors, you have to say a lot that we're not trying to compete with what this expert community has already done. So it's really a demonstration of like this can be done, this is interesting. And kind of linking back to what we have said, there's kind of, I talked about this joint optimization between model accuracy and performance. And like when I was doing this, I would train a model on my laptop, see the loss go down or not go down, take it over the quadcopter, actually try to fly it, and like it was like throwing darts at a wall, whether or not it was actually going to work. So there's not like a clear like, okay, this data made it better. It's kind of like a dark art where we don't really know if it's going to work, and the loss number is not that indicative. And there was a question in the chat, but it's already been answered, which is great. Someone was asking who makes Crazy Flies, and it's a company in like Switzerland or something called Big Craze, which is fun. So I did this, some cool takeaways, and then I was like, okay, there's another year. I'm kind of funded to work on the Ionocraft. Let's go back to the Ionocraft. And I got a couple of Ionocrafts assembled. This was one. This is how a couple hours of my life ended, which was good. For anyone that doesn't know, it's not supposed to be like that. We want it to fly, but I was happy digging this photo up, which was pretty funny. And but I did assemble a few of them, and eventually there was a few people here, like Mauricio might have been here because it was a high-speed camera, but I got like one good video on like my second one, and I've milked a lot out of this video. We don't actually know if we can call it controlled flight because the wires are wire details that I won't go into, but it looks great. And that's as far as we got to trying to use some sort of model-based RL to actually control the Ionocraft. But I think then I went off and did an internship, and there's other factors that made me not come back to this. But this is a cool video. This robot is using like 2000 volts to generate ions moving through the air and hover completely silently. So I'm just going to take my moment to watch that again. Okay. So this is all kind of where the talk will transition out of talking about robotics and more into kind of this work that I've done in model-based reinforcement learning. And it's around this issue that we called objective mismatch. So I've talked about a certain like linkage or lack of link, and it's between like the accuracy of the model and the performance. And if you're trying to learn a dynamics model from control, your intuition is that those are going to be closely linked. And what you're going to be looking at in practice is that you'll do something like maximizing the log likelihood, which is a metric for if you're learning a distribution of transitions, and you'll want to see that your like episode reward, so the cumulative reward that your agent receives, is actually maximized. And you want to see if these are correlated. And in practice, we've shown that it's definitely complicated. To do this, we went back to kind of the model learning for control origins. And if you take a simplistic view of system identification, what happens is that you're trying to obtain like a task agnostic and like locally global model of your environment, and then learn a controller. So you'll do something called this illustration here is supposed to illustrate like what is called elicitation trajectories, where you could take a bunch of actions to cover the entirety of your state space and hopefully get the right data to be done collecting data and just have good controllers. And in reinforcement learning, it's inspired by this, but in actuality, it doesn't translate it directly. So what happens is we observe a task-specific subset of the data, and we're repeatedly exposing ourselves to a changing distribution of that same part of the state space. So we kind of have a lot of the same data over time, and we're just throwing more computation power at learning the same thing with a little bit of interesting other data sprinkled in. So there's a big difference between collecting exactly the data that you want and some automated exploration path that generates data close to what you want. And we're kind of trying to understand, is that limiting us in terms of the downstream performance? So if we revisit this model-based reinforcement learning loop that I talked about in the past. So here we have some policy pi that interacts with the environment, and this is going to give us some set of data. This data is going to be transitions, which are states and actions, and then reward, which is kind of the notion of how well we're performing in the world. And what happens with these trajectories is that we're going to train a dynamics model that's going to just kind of be based on the properties of the state transitions. And what we kind of noticed was the missing factors in terms of joining this into one effective system was what we called these objective mismatch arrows, where we want the reward that we see to inform our policy decisions and our dynamics model. So, and the question is like, how bad is this and what can we do about it? At a really low level detail, if you were to try to implement this algorithm I talked about, what you'd see is that you kind of have these two optimizations, one at training time and one at control time. And even though you kind of want them to work together towards the control outcome, the parameters are generally totally not linked in any way. And that's what's causing this weak signal of correlating accuracy between performance. So that's what we call the objective mismatch. So if we revisit this assumption of model learning for control, which is that if we improve the accuracy, we'll get higher performance, we'll get higher reward. We wanted to look into seeing if this is true. So if we kind of visualized this trend, we could draw a sketch where we have a plot between likelihood and reward. And what we would expect is a really tight relationship where as the accuracy improves, the reward improves. So kind of the key things to look at here are that we would expect this line to be monotonic and also the points really clustered to it. A noisier set would be less clear, which would also be a lower correlation. So what we did is that we then took a few different data sets. We took dynamics models that we ran on a model-based RL task. So we let agents learn in the environment. We collected a bunch of dynamics models and we wanted to see their accuracy across different data sets of interest. And those data sets of interest kind of link back to the motivation for this project to start with, which are like, what are the actual differences in the data sets between model-based RL or on-policy learning, which is kind of this iterative approach, versus something like system identification that's a really global approach. And then also we can trim down the on-policy data into something that's called expert data, where if you just take the trajectory of the one agent that did the best, what does that behavior look like? And we can look at different correlations between accuracy and performance across these different data sets. So I'll kind of populate them in the same locations that the previous slide was on. And for example, this is on a really popular task called Half Cheetah, which is this weird amoebus 2D joint thing. And that's a very common task in our field. And what we did is we collected these different data sets and we kind of started populating a lot of trials to look at this accuracy versus reward. So here you can kind of look at this and think that it's maybe okay, and the noise is really the issue. So if you pick like a point, if you pick a point on your x-axis like 2, then the range of possible outcomes on your y-axis is so high that as an engineer, it's like we want guarantees, we want bounds and things like this, and there's really no bound on how bad there's the bound for how low your performance can get is pretty much 0 at any given accuracy. So it's not very useful to see this. And then when you look at the expert or the global data, it's really that the models trained in the act of learning do not translate to the specific task that you learned. So expert would be like, okay, what is the best an agent can do with the task? Most of the dynamics models don't actually get very high accuracy on that. And whether or not you can model that is not well correlated with your final performance. And global takes this kind of trend even further. Global is we took data points across the whole state action space. So it's like a 20-dimensional volume, and then look to see what the predictions look like on that space. And again, they're just really not accurate and not correlated with performance. So this is kind of just like the first glimpse into the fact that a dynamics model's accuracy is not actually a useful signal to an engineer that's trying to really precisely get a high performing system. And a more fun way that we looked into this is to perform something called an adversarial attack on a dynamics model. So what we did is we took a dynamics model from an agent again, and we took the output layers of the neural network. So think just like some values in the matrix of the neural network. And we took another optimizer to try to make the agent have low performance, but still having high accuracy on a held out set of data. So this is kind of one of the favorite experiments of my PhD, because it's just kind of out there, but I think the intuitions that we'll get to are really interesting. So we wanted to see if we could use some computing power to show objective mismatch by finding models that don't perform well at the task, but are quote unquote high accuracy. So what we did is we used an optimizer that's like covariance matrix adaptation, which is like an evolutionary algorithm to actually fine tune the output layer here. And what happens is on this different task, this one's cart pull, which is an even easier task, we could push the reward down by like 50% of the original performance of this model while still maintaining the same neighborhood of accuracy. And this is when I started to get some relatively deep intuitions about what is happening in these dynamics models. And it really has to do on like, I think of it as like a density of how dense the space of good models is versus the space of accurate models. And there's a lot more accurate models than there are accurate models that are actually good for control. And if you think about a low level, this is now going into unproven territory, but if you look at stochastic gradient descent, what you have is like a batch of like 32 states, and your loss is based on like the average of those 32 that you compute. And in reality, for control, only like one of those states will be really important to your controller, but it's getting averaged out by all these states that don't really matter. And that is causing the accuracy to be quote unquote better, but the performance can go down. So that's a mechanism that if anyone wants to look into it, great. It's definitely hard to look at what stochastic gradient descent is doing, but it would be really fun to look at. So then the question that any computer scientist will ask is like, okay, what can we do about this? And in different pieces of my work, we've kind of worked on this in 2 ways. First one is to just redesign what a dynamics model is predicting, which is kind of a proxy way to address it because we're not changing how this gradient descent is performed. But we also did retune the gradient descent a little bit to actually like, okay, if we think that we're not optimizing the right states, what if we prioritize states that are close to the task that we want? And that does actually improve sample efficiency and performance. And don't go down that whole path in this talk, but the dynamics model is a bit simpler to explain, and I will go into that here. So this paper is something that we call the trajectory-based dynamics model. And kind of instead of taking in a state and an action to predict a next state, what we wanted to do is directly include some notion of time. So the input to this model, so F theta here is a parameterized model where we have some starting state, some prediction horizon, which is that notion of time. And kind of in order to trade off, to get this in direct notion of time, we needed to change how the actions were inputted to the model. And in this case, we input the control parameters. So all the actions are actually a function of the control parameters. So if we can pass the control parameters in directly, maybe we can get better properties. There are some limitations with that I don't need to tell you. And what you get is that you get a bunch of advantages in how this model works to try to map to our specific goal of getting more accurate predictions that might be more useful for model predictive control. So it ends up being that there's better long-term prediction accuracy. And in terms of deep learning, it actually collects data points about twice as fast, like quadratically, because we're relabeling on each sub-trajectory rather than each step. So with the models I talked about earlier in this talk, if you have a 10-step line, you get 10 data points. And this, you'll get something like 90, or it's actually like 45 if you get a factor over 2, because you're labeling each transition from 1 to 2, 1 to 3, 1 to 4, 1 to 5, and then like 2 to 3, 2 to 4, 2 to 5. So you get these sub-trajectories, which is kind of a interesting emergent factor of using this model. I don't know if that was the original design at this point, but and that does help with learning efficiently. And then because we have an explicit prediction horizon, we can take a GPU and we can pass in a vector of time, and we can predict the whole future in one forward pass rather than needing to do this recursion, which is related to how you get this better long-term prediction accuracy. And then kind of a more subtle but interesting point is that the uncertainty in our predictions more closely mirror the empirical uncertainty in the data set. Again, when you're doing this recursive prediction, you end up getting kind of this growing error bound that's not really useful for control. So there's a lot of advantages here. There are some more difficult implementation things to overcome, kind of like these control parameters that you have to pass in. But that's all for future work, which I don't have to talk about because this is an easier talk than that. And kind of at this point, it kind of like really broadened my interests in my PhD. So this conclusion will kind of take a left turn again, which would be fun. So if we revisit this sample-based model predictive control kind of loop that I talked about, the question that I'm kind of interested in is like, what is this actually doing and why? So for example, one thing that we don't really know is like how exploration is done with this. So if your dynamics model is inaccurate everywhere, you propose a bunch of actions, you're essentially selecting random actions. But if you ask someone in practice, they don't actually think that it's exactly random. So something more nuanced is going on in how these agents accrue data points at the fringe of what they have experienced. And the fact that no one really knows that is really interesting to me. And it's kind of raises the question of like, are these agents that we're trying to send out into the world reliable at all? So if we go back to a plot like this, you can see that there's like the chosen action sequence that we took from the model, and then what would actually happen in the real world in black if you actually did this. And then there's this big gap, and like, what is the cause and effect of these errors, to put it simply. And that's something that I've been starting to work with, especially as we kind of think about taking artificial agents that are really powerful into the real world. So there's been a series of high profile successes from mostly Google companies, honestly, which is a little sad, but they're starting to do things that people didn't think were possible, and well before they even were going to consider them. So like, you talk to the AI safety literature, AI safety people, AlphaGo happened years before they expected it. So that's kind of a data point on where things are going in the field that kind of is powerful to me. And then what actually enabled these technologies? A lot of the successes are kind of enabled by this loop of reinforcement learning that I talked about. So kind of this trial and error learning, but they're also scaling it up to a level in industry that as academics, we don't really have as much access to. And then if we think about what these agents are actually going to be doing in the real world, we're trying to translate from something like a game, which is known exactly what the dynamics are, and to these unstructured and kind of dynamic domains. So if you come up with a bunch of them, I could throw these all out at you with autonomous driving, like physical sciences, financial markets, all these really high dimensional complex problems. And in reality, most of them are well underway. So Tesla's documented saying that they use a version of the same algorithm that AlphaGo grew into to control their cars. And DeepMind is now working on like biological folding, fusion reactors, like these things are all happening. And there's really big questions around whether or not these agents are actually reliable. So if you want to look for it, you could certainly find machine learning failures from systems that already exist and have been existing for years, whether it's a safety failure or some other type of fairness failure. And what we're doing is adding a notion of like a dynamics into this, where we're adding characteristics of these systems that are already not well understood to real world domains that have really high impact. And what I'm kind of interested in is what is the intersection between developing cutting edge algorithms, but also understanding how to more precisely control their performance in the real world and make good systems. So reinforcement learning systems at brief are prone to exploitation and kind of like have this temporal aspect. So if you look in this boat, Coast Runner is really famous. It was supposed to be training an agent to actually race around a course, and it got more points by doing this. And it's now really famous. And this is some work that Roberto and I worked on where we applied AutoML to existing model-based RL algorithms, and it just like destroyed every other paper's scores to date. So it's like, okay, there's a lot of power that's currently untapped and people are kind of looking in different directions. So what I want to do is like, okay, yes, I want to make machine learning systems in the wild that are autonomous, but kind of make them legible and actually understand what's going on. I don't really want to use words like AI safety or fairness or all these things, because they're all off in their corners. We kind of we need to have discussions at the boundaries between these already existing fields when we're building these systems. So I can show you kind of the last, like how I've been starting to view this is that there's different notions of feedback in a reinforcement learning system. So there's the bottom half, which I showed you a few times, which is kind of this notion of control feedback, where you get a state and you use that to then take an action. But also what these agents are doing is they're taking their past experience and their current policies or parameters and using that to determine their future behaviors. And that sort of behavioral feedback is kind of core to what this line of work was inspired by, which is kind of like biological learning and kind of like behavioral science. So the things that I'm currently trying to figure out is like, how do these agents actually fail? So as there's a lot of appetite for fair systems and long-term safety of AI, there's kind of something in the middle, which is kind of a few thought exercises I've come up with, which is like, if you have a desired trajectory, it's like, why does one crucial action diverge from that? It's really hard to look into these systems and understand what the specific error was that caused one wrong decision. And then also, like, if you're having an agent that runs for a long time and you expect it to encounter a bunch of different behaviors, what is stopping that from achieving a undesired positive behavior or an undesired negative behavior? It's like, what is keeping these agents on a track towards the behavior that the designer desires and versus a starting point? And these are things that are really not well known. And what I want to do is kind of continue to understand model-based RL, because we'll have this notion of dynamics in the world, and we can kind of use that to build algorithms that are useful and ones that we can also understand. So that's the end of the academic part of my talk, but I have more to say. So I'm going to keep going. And generally, this PhD has been a part of many people's lives, which is pretty amazing. And I kind of want to just take the space to acknowledge everyone that has been through COVID with this, because like Ani's here, we're kind of coming back, and there's a lot of people that just kind of left grad school without celebrating and doing this as much as I think everyone wants to. And like, even I was on that track until like a few weeks ago, when like my parents came out last minute, and I was ready to just kind of like pack up and leave, but it's like clear that there's appetite from the community to kind of like come back and keep doing grad school as it was when we started. So I'm excited to see everyone here and just kind of like acknowledge that we should make sure everyone celebrates their way out and people aren't just kind of piecing out the semester because that's what everyone was used to. Because I almost did it, and that's pretty sad. But I talked to a lot of people in my PhD, and this is people that I have published with. There's definitely other people that played a big role in this. So I can kind of start by thanking my advisors. It's definitely been a journey, but I really appreciate that you guys kind of just let me do me, and we're like, we made it work. And that's a huge accomplishment. And there's kind of a different hurdle at all the times, but we kind of kept going in the right direction. And I think it was successful at that. And from advisors kind of come a research group. So Chris's group, I worked and wrote papers with way more people than I would have expected when you kind of hear the intro or the things that I talk about, if you know Chris's group or my background or anything. So I don't know how many people are on the call, but there's certainly some people on the call that I appreciated working with everyone, and it kind of learned how to do science, but work in this like jet fuel field of machine learning, which is kind of an unusual balance there. And I wanted to give a shout out to some people in the student group Geese. I know a few of them are on the call, which is kind of where I started working on this intersection of machine learning and society. And a few of them are, I think there are people on this virtually, but I joined when my PhD was at kind of a low point in COVID, and it kind of transitioned stuff that I was writing on my blog into real academic work. And then it kind of helped me get jobs. And I'm excited to kind of continue to make this line of work with you all. And then I don't think anyone is paying this close, but this is kind of the collection of people that I published with that aren't Berkeley people. And that's pretty amazing to kind of meet people through internships and work with them, or get drawn into collaborations after internships and kind of work with a lot of different people that all contributed to kind of where I am now. And I'm really appreciative of that. And I know that I'll continue to encounter a lot of these people in the future.